Hello everyone and welcome to our presentation. The activity we chose to focus on is Wii Bowling. So if you're not familiar with the Wii, it's a gaming console. It's about 10 years old and it works on motion sensing technology. So you have a controller and depending on how you move that controller left, right, down, or up, your little Wii character, which I think they call him me, will kind of reciprocate how you're moving that controller. So if you have a bowling ball and you have the controller in your hand, you move the controller up, the ball will go up. You move the controller down, the ball will go down. So again, it's motion sensing technology. So our description of our project. So the activity we chose is bowling, and we thought a pretty natural way to look at learning or ability in this domain would simply be the score someone gets when they bowl. We expect a master bowler to consistently score high, and we expect a beginner to probably score lower. Importantly, our trials that we conducted, we only measured the results when there were 10 pins. So if someone went and knocked down, say, 7 pins, and there were 3 pins remaining on their second try, we just threw it in the gutter and did not count that as an observation. So for the purposes of this study, to create standardized conditions, we only counted an attempt or a trial as a trial when there were 10 pins. So what we did is we designed a training intervention. We had a friend who was really good, always scored above 150, which is a good score in bowling. And he came in and he watched us bowl 5 turns in a row. And after he watched us bowl, he took note of what we were doing wrong or maybe what we could improve. And then we had a training intervention that lasted about 3 minutes for each person. This training was delivered verbally, and he just kind of coached us on the motions that are involved in a good bowling swing. After the training, we then bowled and we took post-training scores. So before the training, we bowled 5 times. After the training, we bowled 5 turns. And we have 5 pre-measures and 5 post-measures of our ability. And again, this is how we're assessing learning someone's score in bowling, which is defined as the number of pins they knock down. And we used a paired t-test to look for significant results. So how do we use the kinetic sensor? So the kinetic sensor, we actually taped it to our arms. This is on our phone. So we taped the phone to our arms and we would push start recording on the acceleration part of the app right before the motion was started, and then after the motion was ended, we would hit stop. And scores were recorded separately while the acceleration data was being logged by the app. Acceleration was measured in 3 directions, X, Y, and Z. So X acceleration would be side to side based on how we attach this to our arms. We would expect there to be little effect of sideways acceleration on bowling scores because a bowling motion, it goes back, goes down, and then goes through, kind of up and down and forward and back. So Y measures forward and back. We would expect this acceleration to be important in a bowling swing. And particularly, the faster you accelerate in the direction of Y, the more force the ball would have. Z is up and down. The same is true here. The greater Z acceleration you have, the more force the ball should have. Whereas X, side to side, perhaps isn't the best measure in bowling. So our data analysis. We did a few things. We did paired t-tests to see if there was a significant improvement after the intervention. We did a correlation plot to see what was associated with high scores. We took a visualization approach to building bivariate models. Then we did some time series and clustering analyses. Study measures. We had 6 individuals. So there were 6 people in our data set. There were 10 trials for each of us, 5 pre-measures, 5 post-measures. And we just numbered the trials 1 through 10, so that created a variable. Then we had pre and post scores. We had X, Y, and Z accelerations. Now for each of these, they were recorded in a time series manner such that in a single second, we might have like, say, 50 observations of X acceleration at, say, 0.1 seconds, 0.12 seconds, and so forth. So the main thing we did to collapse all that and make it more usable was we took the mean acceleration per motion. And then time of bowling motion. So some people would have very quick motions where they just went back and threw the ball very quickly. Other people had longer motions where they kind of stepped back, stepped into it. They range between 1 and 4 seconds, these motions in our study.
So because everyone moves a little bit before and after they throw the ball, we need to clean the data to get rid of those motions not related to the bowling. So here we only pick the data within the red box, and you can see that you can see the clean data in the right figure.
Paired t-test. So with 60 observations, there were 30 pre and 30 post. This makes for an N, or a sample size, of 30. You can see the pre-test mean as 7.24. This means on average, before the intervention, we knocked down 7.24 pins out of 10. On the other hand, the post score was 8.36. This means on average, after the intervention, we knocked down 8.36 pins. This is an improvement of about 1 pin. The question is that significant? We have a t-statistic to do our hypothesis testing here. We observe a significant p-value of 0.026, which would give us evidence to say that this intervention did significantly improve our performance. Note that all of the bowlers that used the Wii had no prior experience in bowling other than myself, who owned the console. So it's what you would expect, right? Cohen's d, a measure of effect size. It's simply the mean difference, 8.36 minus 7.24, divided by the pooled standard deviation. 0.65 is judged to be a large effect size as per Cohen's advice. So we also wanted to look at a correlation plot, which would tell us how getting a high score was related with other study variables. We see that, like we would expect, acceleration in Y was the strongest correlation. This is acceleration forward and back. The more acceleration you have in the Y direction, the more force the ball would have on it. Z acceleration, this is also true, but to a lesser extent. Z's up and down motion. You go back in a bowling motion, and you go down and forward. So a moderate correlation in both the positive directions with Y and Z. We actually observe a negative correlation with X in score. It makes sense. As you do not throw the ball straight down the lane, your score is deteriorating. We took visual approach here to our model building. We have score on the y-axis, X acceleration, and just like that negative correlation we saw, we see it's borne out here in the data. There's a negative relationship between X and Y, where Y would be the score. For Y acceleration, which had the strongest correlation, we see a clearly positive acceleration. And do remember that these measures of acceleration, they're the average acceleration throughout the whole motion. And we had to do that because of the time series nature of the data. Also note that we use the technique called jittering. So technically you cannot get a score of, let's say here, this little data point, 5.1. Because our Y variables were discrete, they were only whole numbers or integers, all of our data points are stacking and sitting on top of each other. So there's a argument in the ggplot package called jitter, which adds a random amount of noise in the X and Y directions so that your data points aren't sitting on top of each other. It's a useful tool for those of you who are not familiar with it. Z acceleration, we observe a positive trend. No, highly nonlinear, but still positive, like the correlation plot suggested. We also looked at the average score and how that relates to the time of motion. Again, we had some people with very fast motions of 1 second. Other people took 4 seconds. We noticed nonlinearity here such that there seems to be a sweet spot here in the 1.5 range. And then again, as you approach 4 seconds, scores are again rising. If you're going bowling, at least on the Wii console, having a release time of 2.5 seconds perhaps may not be optimal. Also, very short at 1 second, perhaps not so good. So these are the overall patterns for every bowler. Now, these mask important individual differences. I mean, you can tell the slopes are crossing. So this tells us there's a very different response in terms of score and response time. Also notice that some people, they had motions that ranged from 2 seconds to 4 seconds, but didn't really have any shorter. Other people kind of had more variability in terms of the release. So again, the overall relationship we plotted on the previous screen is masking important individual differences. In terms of clustering, this is a little hard for us to interpret, but we see some general patterns. So what we did is we took all the variables and we made clusters. We chose 3 groups, and these 3 groups are here: cluster 1, cluster 2, and cluster 3. And we then plotted those on an x and y coordinate system where we have score along the y-axis, and then the x-axis is alternating between the different accelerations we have, x, y, and z. So in general, you can see the green cluster. It was kind of a lower score and a lower acceleration in terms of all of these things. You can see how it's more similar than the red and the blue clusters. They're kind of all on that left side. You can also observe a kind of slight positive slope for all these green lines. Now the blue cluster, we think it would have been better to go with 4 data clusters, because you can see the blue is really should be 2 clusters. So this middle line is just not a good representation. We see the same thing over here. Again, the blue cluster is really just so spread out here. And this line is probably not really accurate for that. The red, kind of the opposite of the green. It was kind of in the top right corner of most of these, with the exception of Z. So again, a little hard to interpret, but there's some meaning in our clusters here.
And another way to look at data is we look at how acceleration change with time. We believe it could probably give more insights about how to become a good baller. So here the x-axis is the time and y is the score. And we plot the change of time series with its score here, and you can see, well, obviously the acceleration will go up and down quickly. And then we use cross-correlation coefficient to measure the distance between each time series. And this is similar to the concept of distance in clustering analysis. And K-means clustering algorithm give us 4 clusters here, and well, we pick number 4. So we have 4 clusters here, and the pink and the black have a lower average score, which is 6.8 and 7, and the dark blue and light blue clusters have a higher average score, which is 8.4 and 7.9. And we can see the pink has a very short duration of motion, and the black has a very relatively longer duration, and the dark blue and light blue have like the duration in the middle. And compared to what we have, the relationship between scores and time here, we will conclude that if you want to get a higher score, you'd better keep your motion within about 1 point here, about 1.3 to 1.75 seconds, which is also the range here. So you would have a theoretically you would have a higher score than if you throw the ball in longer or shorter time, like here and here. And this shows the 4 clusters. For each cluster, this time series should be very similar, and you can see that from here.
All right, so this is just a picture of our pre-planning. So just to summarize what we've done, we measured learning in a bowling experiment by the scores that someone gets when there are 10 pins present in each trial. We then did an intervention to see whether an expert training might be able to improve our bowling scores. We found that it did. So again, we measured learning through scores, and we did all kinds of things from clustering and time series analysis, and then our statistical inference was done with the t-test. Thank you all for watching our video. We hope you enjoyed it. Bye.